Hi, today I'm going to talk about privGAN, a novel privacy-protecting GAN architecture. Dataset sharing is hard but essential. Sharing data publicly or between institutions leads to innovations such as development of new machine learning models, drug development, etc. However, such data can often contain private information about individuals, which can be misused by malicious actors. Therefore, there is a huge need to develop privacy-preserving techniques to share data between institutions or publicly. One potential solution is the use of synthetic data. Recent progress in generative machine learning has led to models that can generate realistic synthetic data after training on a real dataset. An example is shown here. The leftmost image is a real image, and the two left images are generated by GANs. As you can see, the fake images are quite like the real images. The idea with synthetic data is that the synthetic data sets can be used to train models for downstream machine learning tasks such as regression, classification, etc. And the naive assumption that people had when this practice became common was that since samples are synthetic, each sample does not leak information about real people. However, this is an incorrect assumption, and I'll explain how. To do that, I'll first need to describe what a membership inference attack is. A membership inference attack is a privacy attack where an adversary with access to many samples wants to just simply know whether a sample was used to train a machine learning model or not. The adversary has some access to the trained model, query access, and uses this query, the query output for each sample, to predict whether or not the sample was used to train the machine learning model. So why would such an attack work? For attacks like this to work, the query values for samples used to train the model should be very different from samples that were not used to train the model. And as most of you who have worked with machine learning would know, that this happens a lot. Overfitting of models happens a lot in machine learning, particularly as model complexity increases. And hence, the training set sample, the query output for training set samples are quite often quite different from the samples that were not used in training, making such attacks very powerful. Okay. So let's take a quick diversion to first to define what a GAN is. GAN stands for Generative Adversarial Networks. Generative Adversarial Networks are a broad family of generative machine learning models, and they usually comprise of two machine learning modules, a generator and a discriminator. The goal of the generator is attempt to generate realistic data, while the discriminator attempts to identify fake samples from real samples. So the process of training these two modules reduces to a two-player game between the discriminator and the generator, and eventually the generator succeeds in generating samples that are indistinguishable from the real, or in other words, it learns the data set that the real samples are drawn from. So how can such a model overfit to the training set? To demonstrate that, let's look at this experiment. Here we plot a histogram of the discriminator scores. A quick reminder, the discriminator is just a binary classifier for real versus fake. So its output is a number between 0 and 1. So we plot the histogram of the discriminator scores for samples that were used to train the model, shown in red, and samples that were not used to train the model, shown in blue. And as you can see, there is quite a large discrepancy between the distributions, to the red and the blue distributions. And this is even larger in Fashion MNIST compared to MNIST, since Fashion MNIST is a more complicated data set. And as one might imagine, since there is such a large discrepancy between these two distributions, an adversary that relies on this difference would be quite powerful. So what are the existing solutions to this problem? The most common class of existing solutions are differentially private GANs. As most of you might know, differential privacy is a way to bound the privacy of algorithms, not models, and it leads to strong formal guarantees. It involves the addition of noise to gradients during discriminator training, as in DPGAN, or adding noise to labels for discriminator training, as in PatowArY. The problem, however, is that this leads to very poor synthetic image quality, as demonstrated in this example here. So the leftmost set of images are real images, whereas the everything right of it are synthetic images. And as you can see, as you decrease the amount of privacy, epsilon here, you eventually get to a point where the samples are quite realistic. However, only for the rightmost column, where the images are horribly corrupted, is the privacy parameter epsilon even in a realistic range to provide a usable privacy bound. Everything left of it provides a privacy bound that is so loose that it's almost as good as not providing a bound at all. This brings us to our solution, privGAN. privGAN is much like a regular GAN. It contains of generator and discriminator modules, but instead of one generator and one discriminator module, it contains multiple generators and discriminators. So the way it works is the dataset is initially randomly split into two or more non-overlapping parts. Each part of the dataset gets a generator and a discriminator. The goal of the generator is now to fool not just its corresponding discriminator, but an additional module called the privacy discriminator. The privacy discriminator looks at synthetic data generated from different generators and tries to tell them apart. And the generator's goal is to therefore generate synthetic data that somehow has the characteristics of the overall data set and not just the portion it's being exposed to. So this takes the form of a multiplayer game, and it can be shown that the effect of adding the privacy discriminator is mathematically equivalent to providing a regularization of sorts, and it bounds the distribution learned, the synthetic distributions learned by each generator. So the overall outcome of this process is that privGAN prevents generators and discriminators from overfitting to any data split. So how private is privGAN? So coming back to our previous example of on the same data sets that we showed that the non-private GAN horribly overfits to the training set, we can show that privGAN has multiple discriminators, so we choose one of the discriminators on random, and we perform the same experiment, and we show that the difference between the distributions of distributions blue and red is much smaller. So discriminator scores for samples that were in the training set versus samples that were not in the training set are very small in the case of privGAN. So an attack that relies on the use of such scores would be very ineffective. So can we show this quantitatively? To demonstrate this quantitatively, we performed experiments against several state-of-the-art attacks in our paper. The one that I'm going to show here is quite similar to the qualitative experiment shown previously. So the way it works is you have data set, you pass the data set, the adversary has a data set, passes each of the samples in the data set through the discriminator, obtains a score for each sample, and then sorts the samples in descending order. The attack also assumes that the adversary knows how many samples were used in the training of the model, say n, and takes the top n predictions. So how successful is this attack? So in the case of a regular GAN shown in red, you can see that as you increase the number of epochs, the white box attack accuracy can go up quite a bit. However, privGAN consistently provides membership privacy protection, at least against this attack here. And we show that in the paper, we show that this is true for other state-of-the-art attacks as well. So how does the hyperparameter choices in privGAN affect membership privacy? privGAN has two hyperparameters: n, the number of generator and discriminator pairs, and lambda, which is how much we weigh the the privacy discriminator module in the loss function. So we show here that as you increase lambda, the white box accuracy decreases on all data sets, and similarly, as you increase the number of generators, you see the same effect. However, it is important to point out that unlike epsilon and delta in differentially private approaches, n and lambda in privGAN are dataset dependent quantities, and they don't have an intrinsic meaning in terms of privacy. So what n and lambda will work best for your dataset is dependent on your dataset and has to be experimentally determined. So as mentioned before, one of the motivations behind privGAN was providing a decent level of performance and downstream utility while providing membership privacy benefits. So to see whether we're able to do that, we performed this experiment where you take various GANs, privGAN, the non-private GAN, and DPGAN, generate synthetic images, same number as the training set, in these various data set, train a CNN-based classifier model on the synthetic data, and then test on the real test set. So you can see in the on the red bar is if you train the CNN model on real data and test on real data. This is obviously the best case scenario. The gray bar is if you use a non-private GAN, and then the three blue bars are privGAN for increasing levels of privacy. We test 0.11 and 10 values for lambda. The green bar is DPGAN at an epsilon of 100, which is a ridiculously high epsilon, but anything below that leads to unusable images pretty much. And you can see consistently that privGAN leads to very little drop in utility compared to the non-private GAN, and the utility is much higher than DPGAN, even for a very high value of epsilon in DPGAN. So far we've shown privacy and utility separately, and shown that privGAN provides both privacy and utility benefits. But what if we compare them simultaneously? So we do that here, where we take various values of epsilon in the case of DPGAN and various values of lambda in case of privGAN, and generate synthetic data and perform the utility experiment, record the classification accuracy, and the privacy experiment and record the white box accuracy. And you can see that across two data sets, we can see that for most values of membership privacy quantified by the white box accuracy, privGAN provides much higher utility measured by classification accuracy in the previous experiment. And so we can show that in most regimes, privGAN is a better alternative to DPGAN, and we performed a similar experiment on Patowary. There are several practical deployment considerations while using privGAN. The first is GAN architecture selection. We recommend performing architecture selection on the non-private GAN of your choice, and then use the same discriminator and generator architectures for privGAN. The privacy discriminator, which is the additional modules found in privGAN but not in other GANs, is simply a minor modification to the regular discriminator modules, and requires a modification in the final layer as described in the paper. Another consideration might be membership privacy certification for both the model and the synthetic data sets. We recommend using either state-of-the-art attacks as query-specific empirical certificates, or using formal query-specific membership privacy certification mechanisms as described in our follow-up work below. Finally, privGAN has two additional hyperparameters which affect both privacy as well as utility. We recommend users to identify their desired utility and query-specific privacy levels and perform a grid search to identify appropriate values of n, the number of generators, and lambda that provide the desired utility and privacy levels. And this too can use the framework cited below. In summary, privGAN is a novel membership privacy protecting GAN architecture. privGAN can effectively protect GANs against state-of-the-art membership inference attacks shown in our paper while maintaining high quality of generated samples. privGAN compares favorably in terms of privacy versus utility against other privacy-preserving GAN approaches such as DPGAN and PatowGAN. And here's the link to our repo. Thank you.